A massive black hole lurks closer than anyone expected. Astronomers just traced 21 stars moving at impossible speeds, and what they found rewrites everything we thought we knew about our cosmic neighborhood. Half those stars were fleeing from something we never knew existed. For decades, scientists believed they had mapped the gravitational landscape around the Milky Way with reasonable confidence. Our galaxy's central supermassive black hole, Sagittarius A star, sits about 26,000 light-years away, holding court at the galactic center with a mass of roughly 4.3 million suns. That number alone seems staggering, but in the universe of supermassive black holes, it's actually modest. Some galaxies harbor monsters weighing billions of solar masses. Ours seemed relatively tame. Then researchers started tracking hypervelocity stars. These aren't your typical stellar objects drifting through space at comfortable galactic speeds. They're moving fast enough to escape the Milky Way entirely, racing toward intergalactic void at velocities that defy normal stellar behavior. 21 of these cosmic runaways were traced with ultrafine precision using data from the European Space Agency's Gaia mission, a space observatory that's been revolutionizing our understanding of stellar motion. The team expected a straightforward result. When you find stars moving that fast, you trace their trajectories backward to find the gravitational slingshot that launched them. About half the stars pointed exactly where predictions suggested, toward Sagittarius A star at our galaxy's heart. Binary star systems that wandered too close to that central monster got torn apart by tidal forces, with one star captured into a death spiral while its companion was flung outward at millions of miles per hour. But the other half? They came from somewhere else entirely. The trajectories pointed toward the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way at a distance of roughly 160,000 light-years. It's one of our closest galactic neighbors, visible to the naked eye from the southern hemisphere as a smudge of light that ancient cultures incorporated into their mythologies. Modern astronomy revealed it as a dwarf galaxy containing several billion stars, swirling through space in a slow dance with our much larger Milky Way. Nobody expected it to harbor a supermassive black hole of its own. The discovery emerged not from direct observation but from detective work. Those hypervelocity stars became cosmic breadcrumbs, their trajectories preserving the memory of their violent ejection. When researchers combined Gaia's precise positional data with new theoretical models describing how binary star systems interact with supermassive black holes, the conclusion became inescapable. Something massive lurked in the Large Magellanic Cloud, massive enough to accelerate stars to escape velocity through the same mechanism operating at the Milky Way's center. This changes the gravitational architecture of our local galactic group. The Large Magellanic Cloud isn't just a collection of stars loosely bound together. It's got a gravitational anchor at its core, a central engine that's been shaping its evolution for billions of years. That black hole has been sitting there the entire time, invisible to direct observation, betraying its presence only through the stellar victims it's been flinging into the intergalactic void. Think about what that means for a moment. We've been studying the Large Magellanic Cloud for centuries. Astronomers have cataloged its star clusters, measured its rotation, analyzed its chemical composition, traced its orbital path around the Milky Way. Yet this fundamental feature of its structure remained hidden until researchers started asking why certain stars were moving impossibly fast. The universe keeps reminding us that even familiar cosmic neighborhoods hold secrets. The mechanism behind hypervelocity stars is brutally elegant. Binary star systems are common throughout galaxies, two stars locked in mutual orbit around their shared center of mass. These pairs can remain stable for billions of years under normal circumstances. But approach a supermassive black hole, and stability becomes a luxury they can't afford. As the binary system falls toward the black hole, tidal forces grow stronger. These aren't uniform gravitational pulls but gradients, differences in gravitational strength across the distance separating the two stars. The closer star experiences stronger attraction than its more distant companion. Eventually, this differential force exceeds the gravitational binding holding the pair together. The system tears apart. What happens next depends on orbital mechanics and angular momentum. Typically, one star gets captured into a tight orbit around the black hole, its fate sealed as it begins a slow spiral toward the event horizon. The other star receives a gravitational kick, absorbing the orbital energy of its former companion and converting it into linear velocity. That kick can be substantial. We're talking speeds exceeding 1,000 kilometers per second, fast enough to escape not just the immediate vicinity of the black hole but the entire gravitational well of the host galaxy. These ejected stars become travelers through intergalactic space, carrying within their trajectories the signature of their violent birth. Trace that path backward with sufficient precision, and you can identify the black hole that created them. That's exactly what happened here. The Large Magellanic Cloud black hole represents more than just an addition to our census of supermassive objects. It raises questions about black hole formation and growth in smaller galaxies. Current models suggest that supermassive black holes and their host galaxies evolved together through cosmic history, with the black hole's mass correlating with properties of the galactic bulge. But dwarf galaxies like the Large Magellanic Cloud don't have prominent bulges. They're more irregular, less structured than spiral galaxies like our own. So how did this black hole form? Did it grow from a stellar mass black hole that somehow accumulated material over billions of years? That seems unlikely given the limited mass available in a dwarf galaxy. Did it form from the direct collapse of a massive gas cloud in the early universe? That's possible, but such formation mechanisms are thought to be rare. Or perhaps the Large Magellanic Cloud once hosted a much larger galaxy that merged with it, leaving behind the central black hole as a remnant. Each possibility opens different implications for galactic evolution. If smaller galaxies routinely harbor supermassive black holes, our models need adjustment. If this black hole represents a rare exception, we need to understand what made the Large Magellanic Cloud special. Either way, the discovery forces astronomers to reconsider assumptions about how black holes and galaxies relate across different scales. The detection method itself deserves attention. Gaia launched in December 2013 with a mission to create the most precise three-dimensional map of our galaxy ever produced. It measures the positions and motions of over 1 billion stars, tracking their movements across the sky with unprecedented accuracy. That precision makes projects like this possible. Without Gaia's data, those hypervelocity stars would remain just unusually fast-moving objects without clear origin stories. But raw data isn't enough. You need theoretical models to interpret what you're seeing. The researchers developed new frameworks for understanding how stars travel after being ejected from binary systems. These models account for the complex gravitational environment around supermassive black holes, the various possible orientations of binary systems as they approach, and the range of velocities that different ejection scenarios produce. When you combine precise observational data with sophisticated theoretical understanding, hidden structures become visible. That's what happened here. The Large Magellanic Cloud's black hole wasn't directly observed. No telescope captured its image or detected its radiation. Instead, its existence was inferred from the pattern of stellar motion it created, revealed through the forensic analysis of stars that escaped its gravitational grip millions of years ago. This discovery method might prove more important than the specific black hole found. If hypervelocity stars can reveal hidden supermassive black holes in nearby dwarf galaxies, what about more distant systems? Could we use this technique to map the black hole population across the local universe, identifying objects too faint or too obscure to detect through traditional methods? The answer depends partly on how common hypervelocity stars actually are. Current surveys have identified dozens of candidates, but the real population could be much larger. Many hypervelocity stars might be too faint to detect, or moving in directions that don't bring them near our solar system where we can study them. As survey instruments improve and our catalog of stellar motions expands, we might find hundreds or thousands more, each one potentially pointing toward a massive object that launched it. That brings us back to our own galactic center, where Sagittarius A star has been the subject of intense study for decades. We've watched stars orbit around it, traced their paths with exquisite precision, used those orbits to calculate the black hole's mass and location. In 2020, Reinhard Genzel and Andrea Ghez shared the Nobel Prize in Physics for proving that Sagittarius A star is indeed a supermassive compact object, with a black hole being the only viable explanation. But even our home galaxy's central black hole holds mysteries that researchers are only beginning to unravel, including recent evidence suggesting it woke from dormancy just 200 years ago. The evidence comes from molecular clouds floating around Sagittarius A star, acting like cosmic mirrors that reflect X-ray flashes from the black hole's past. When this RISM space telescope examined these clouds with unprecedented energy resolution, it detected something previous instruments had missed. The clouds aren't generating their own X-rays. They're echoing an ancient outburst, a light show from centuries ago still bouncing around the galactic center. Think of it like thunder after lightning. The flash happens instantly, but the sound rolls across the landscape for miles, reaching different locations at different times depending on distance and terrain. These molecular clouds caught X-rays from a massive feeding event, and we're only seeing the reflection now because of how long light takes to travel the distances involved. The timing works out to roughly 200 years ago, give or take, when Sagittarius A star apparently devoured a significant amount of material and blazed far brighter than its current dim state. That's the weird part about our galactic center. Most supermassive black holes at the hearts of other galaxies shine brilliantly, powered by continuous accretion of gas and dust. Sagittarius A star barely registers. It's one of the dimmest known supermassive black holes in the universe, only visible because it sits so close to us at 26,000 light-years away. If you placed it at the distance of another galaxy, you probably wouldn't detect it at all. So what changed 2 centuries ago? We don't know for certain. Maybe a gas cloud wandered too close and got shredded. Maybe multiple smaller objects fell in simultaneously. The black hole woke up, fed intensely, then went back to sleep. And we're only discovering this now because the light from that event has taken 200 years to reflect off distant clouds and reach our telescopes. This raises uncomfortable questions about how well we understand black hole activity cycles. If Sagittarius A star can go from dormant to violently active and back to dormant within what might be just years or decades, what does that say about black holes throughout the universe? Are we catching most of them during quiet periods, missing the brief spectacular phases when they truly dominate their environments? NASA's IXPE telescope provided additional confirmation by detecting polarized X-rays from these clouds, a signature that matches reflection rather than direct emission. The polarization pattern told researchers exactly what they needed to know about the geometry of the original outburst and the three-dimensional structure of the clouds doing the reflecting. Multiple independent lines of evidence pointing to the same conclusion. But there's another mystery about Sagittarius A star that recent observations have clarified. The black hole spins fast. According to data from NASA's Chandra X-ray Observatory and the Carl G. Jansky Very Large Array, it's rotating at approximately 60% of the maximum possible speed, which is the speed of light. As it spins, it drags spacetime along with it, warping the fabric of reality into a shape that researchers describe as resembling a football, elongated rather than spherical. You might wonder how we measure something like that. Black holes don't have surfaces we can observe rotating. Instead, astronomers look at how material behaves in the intense gravitational field near the event horizon. The spin affects the innermost stable circular orbit, the closest distance at which matter can circle the black hole without inevitably falling in. By studying X-ray emissions from hot gas in this region and radio emissions from jets of material being ejected, researchers can calculate the spin rate. Different teams using different methods have produced wildly varying estimates over the years, from no rotation at all to near maximum spin. The latest analysis suggests the truth lies closer to the upper end, with Sagittarius A star spinning at roughly 60% of its theoretical limit. That's fast enough to significantly affect the surrounding environment, creating frame-dragging effects where spacetime itself gets pulled along with the rotation. Frame dragging is one of those predictions from general relativity that sounds like science fiction but turns out to be measurably real. A spinning mass doesn't just curve spacetime, it twists it. Near a rapidly spinning black hole, you can't even define a stationary reference frame. Everything gets dragged along whether it wants to or not. This has practical implications for anything orbiting close to the event horizon, affecting orbital dynamics in ways that wouldn't happen around a non-spinning black hole. Star S2, which orbits Sagittarius A star every 15.2 years, provided crucial measurements that helped confirm the black hole's mass at roughly 4.3 million solar masses. But S2 orbits relatively far out, at distances where spin effects are minimal. There's another star, S14, that comes even closer, passing within just 6.25 light-hours of the black hole at its closest approach. Observations of S14 helped refine the mass estimate and provided additional constraints on the black hole's properties. What astronomers really want is to find objects even closer, things orbiting right at the edge of the innermost stable circular orbit where relativistic effects dominate completely. That's where you could test general relativity under the most extreme conditions, where predictions become precise enough that even small deviations would indicate new physics. Recent research has identified a tantalizing candidate, a possible pulsar spinning every 8.19 milliseconds near Sagittarius A star. If confirmed, this would be extraordinary. Pulsars are neutron stars, the ultradense remnants of massive stars that exploded as supernovae. They spin rapidly and emit beams of radio waves like cosmic lighthouses. When one of those beams sweeps across Earth, we detect a pulse. The timing of these pulses can be measured with incredible precision, sometimes accurate to better than a microsecond. A pulsar orbiting near Sagittarius A star would act as a precision clock moving through severely warped spacetime. By tracking how the pulse timing changes, astronomers could measure gravitational redshift, frame dragging, and other relativistic effects with unprecedented accuracy. It would be like having a laboratory instrument placed right where you need it most, in the most gravitationally intense environment accessible to our telescopes. The challenge is confirmation. The galactic center is a chaotic radio environment, crowded with sources and obscured by dust. Detecting a faint periodic signal against that background requires enormous sensitivity and careful analysis. The research team led by Karen Perez conducted one of the most sensitive radio surveys ever attempted of the region, and they found this 8.19 millisecond candidate. But candidate status means more work remains. They need to track it over time, confirm the periodicity holds, and rule out other explanations for the signal. If it pans out, expect a flood of follow-up observations. Every major radio telescope will want time to study it. The scientific payoff from a confirmed pulsar that close to Sagittarius A star would justify significant resources. We're talking about tests of general relativity that simply can't be performed any other way, measurements that might reveal whether Einstein's theory holds perfectly or shows subtle cracks under the most extreme conditions nature can produce. Meanwhile, the Event Horizon Telescope collaboration isn't standing still. After releasing the first image of Sagittarius A star's event horizon in May 2022, they continue refining their techniques and adding more telescopes to their global array. That first image took years to produce, requiring the coordination of observatories across multiple continents to create a virtual telescope the size of Earth. The image shows a glowing ring of light surrounding a dark central region, the shadow of the event horizon. That shadow measures roughly 52 microarcseconds across, matching predictions from general relativity for a black hole of Sagittarius A star's mass. The glowing ring comes from superheated gas spiraling into the black hole at a significant fraction of light speed, friction heating it to billions of degrees until it radiates across the electromagnetic spectrum. But creating that image presented unique challenges compared to the first black hole ever imaged, M87 star, located at the center of the giant elliptical galaxy Messier 87. M87 star is about 1,500 times more massive than Sagittarius A star, and its accretion disk changes over timescales of weeks to months. Sagittarius A star's disk changes in minutes. It's like trying to photograph a squirming toddler versus a mountain. The mountain stays still. The toddler doesn't cooperate. To compensate, the Event Horizon Telescope team developed new processing techniques that account for rapid variability, essentially taking multiple snapshots and reconstructing a coherent image from data that's constantly shifting. The fact that they succeeded demonstrates both the power of the technique and the sophistication of modern data analysis. And now they're working on improving resolution, adding more observing sites, and pushing toward video rather than static images, watching material orbit and fall into the black hole in something approaching real time. The comparison between these two black holes reveals something fundamental. M87 star, at 6.5 billion solar masses, absolutely dwarfs our galactic center. Yet both create similar structures, accretion disks and jets, just scaled to their respective sizes. The physics operates the same way whether you're dealing with millions or billions of solar masses. That consistency suggests we understand the basic mechanisms, even if details remain mysterious. Speaking of M87 star, that black hole sits 505 trillion kilometers from Earth, so remote that its light takes 55 million years to reach us. Yet astronomers image it more easily than Sagittarius A star, which lies practically in our cosmic backyard at just 26,000 light-years distant. Distance matters less than behavior. A calm giant beats a hyperactive neighbor when you're trying to capture a portrait. This reveals something about observational astronomy that textbooks rarely emphasize. The easiest targets aren't always the closest ones. Sometimes you want your subject far enough away that its chaos averages out into something manageable. But here's what really stands out about these observations. Both black holes, despite their size difference, confirm predictions made decades before anyone could test them. General relativity, published in 1915, predicted event horizons, accretion disks, and the bending of light around massive objects. Einstein died in 1955, never seeing direct evidence for black holes. The technology didn't exist. Radio astronomy was in its infancy. Computers couldn't handle the calculations. Now we photograph the things, measuring their properties with precision that would seem like science fiction even 30 years ago. The theory waited patiently for reality to catch up. That patience extended to another prediction. Einstein's equation suggested gravitational waves, ripples in spacetime itself, should propagate outward from accelerating massive objects. He doubted we'd ever detect them. The effect seemed too weak, the required sensitivity too extreme. He was almost right. It took a century and instruments so precise they measure changes smaller than a proton's diameter, but on September 14, 2015, LIGO detected gravitational waves from two black holes merging 1.3 billion light-years away. The signal lasted a fraction of a second, a chirp in the data that encoded the final moments of objects 30 times the sun's mass spiraling together at a significant fraction of light speed. LIGO operates through elegant simplicity. Split a laser beam, send each half down perpendicular 4-kilometer tunnels, bounce them off mirrors, and recombine them. When space-time remains undisturbed, the beams cancel perfectly. When a gravitational wave passes through, it stretches space in one direction while compressing it in the other. The beams fall slightly out of sync. That mismatch creates an interference pattern, a signal buried in noise from earthquakes, traffic, wind, and countless other vibrations. Extracting real detections requires sophisticated filtering and 2 detectors separated by thousands of kilometers. LIGO has facilities in Hanford, Washington, and Livingston, Louisiana. A gravitational wave traveling at light speed takes 10 milliseconds to cross that distance, creating a time delay that helps confirm genuine signals versus local noise. Since that first detection, LIGO has joined forces with Virgo in Italy and Kagra in Japan, creating a global network that's captured roughly 300 black hole mergers. They find one every 3 days now. That detection rate seemed impossible just a decade ago. The universe contains far more merging black holes than early estimates suggested, or we're catching them at distances greater than expected, or both. Each detection adds data points, refining models of how black holes form, how they pair up, and how they merge. Some patterns emerged quickly. Stellar mass black holes, formed from collapsing stars, typically range from 5 to 20 solar masses. Supermassive black holes occupy the other extreme, millions to billions of solar masses. The gap between bothers theorists. Where are the intermediate mass black holes? You'd expect a continuum. Stellar black holes should occasionally merge, creating progressively larger objects. Over billions of years, that process should produce black holes weighing hundreds or thousands of solar masses. We find very few. Some candidates exist, but confirmation proves difficult. Then LIGO detected GW190521 in May 2019, published September 2020. 2 black holes, 85 and 65 solar masses, merged into a 142 solar mass object. 8 solar masses radiated away as gravitational waves, the energy release briefly outshining every star in the observable universe combined. That final mass sits firmly in the intermediate range, the first confirmed example. But that detection raised new questions. How do you form an 85 solar mass black hole in the first place? Stellar evolution models suggest stars massive enough to create black holes that heavy should explode completely, leaving nothing behind. There's a mass gap predicted between roughly 65 and 120 solar masses where black holes shouldn't form directly from stellar collapse. Yet GW190521's progenitors exceeded that limit. Either the models need revision, or those black holes formed through earlier mergers, second-generation objects born from previous collisions. That possibility opens fascinating avenues. Perhaps the universe contains populations of black holes that grew through multiple merger events, a process that could eventually seed supermassive black holes. Speaking of which, supermassive black holes present their own formation puzzle. Sagittarius A star weighs 4.3 million solar masses. That's enormous, but modest compared to some. The black hole at the center of Holmberg 15A exceeds 40 billion solar masses. Phoenix A might reach 100 billion. How do you build something that massive? Starting from stellar remnants and growing through mergers and accretion takes time. You need hundreds of millions or billions of years. Yet astronomers keep finding supermassive black holes in the early universe, existing when the cosmos was less than 1 billion years old. The James Webb Space Telescope discovered one at the heart of galaxy Canucks, LRD Z8. 6, existing just 570 million years after the Big Bang, actively feeding and growing. That timeline doesn't add up easily. Form a stellar mass black hole, wait for it to find material to consume, grows slowly through accretion while competing with radiation pressure that pushes material away, and you can't reach millions of solar masses in 500 million years. Not using conventional processes. Several solutions have been proposed. Maybe the early universe formed intermediate mass black holes directly from collapsing gas clouds, skipping the stellar phase entirely. Or perhaps some black holes grew faster than the Eddington limit suggests they should, consuming material in chaotic bursts that overwhelm radiation pressure. Evidence for super-Eddington accretion exists. The quasar ID 830, observed as it appeared 12 billion years ago when the universe was 15% its current age, hosts a black hole accreting at roughly 13 times the Eddington limit while simultaneously emitting strong X-rays and radio jets, a combination that shouldn't work according to standard models. That Eddington limit deserves explanation. When material falls toward a black hole, friction heats it until it radiates intensely. That radiation exerts outward pressure on incoming material. At some point, radiation pressure balances gravitational attraction, setting a maximum accretion rate for a given black hole mass. Exceed that rate and radiation should blow away the infalling material, choking off further growth. ID 830 ignores that limit, growing 13 times faster than it should, yet somehow maintaining stable jets and X-ray emission. The physics allowing this remains unclear. Current models don't predict this combination. The observation hints at mechanisms we haven't incorporated into our theories, processes that might explain how early black holes grew so massive so quickly. Then there's the mystery happening practically next door. The Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way at a distance of 160,000 light-years, apparently hosts its own supermassive black hole. Astronomers traced hypervelocity stars, objects moving so fast they'll escape the Milky Way's gravitational pull entirely, back to their origins. About half came from Sagittarius A star, exactly as expected. Binary star systems venture too close, intense gravity tears them apart, one star falls into orbit around a black hole while the other gets flung outward at extreme velocity, millions of miles per hour. Standard process. But the other half of these hypervelocity stars originated somewhere else, traced back to the Large Magellanic Cloud. The only explanation that fits involves a previously unknown giant black hole lurking there. The European Space Agency's Gaia mission made this discovery possible by measuring stellar positions and velocities with unprecedented precision. Gaia tracks roughly 1 billion stars, determining not just where they appear in the sky but how they move through space. That data, combined with theoretical models of stellar trajectories, revealed the hypervelocity star's origins. This represents the closest supermassive black hole outside our own galaxy, assuming the interpretation holds up under scrutiny. Follow-up observations will test the hypothesis, looking for other signatures of a massive central object in the Large Magellanic Cloud. If confirmed, it adds another laboratory for studying how galaxies and their central black holes coevolve. That relationship between galaxies and their central black holes fascinates astronomers. Almost every large galaxy contains a supermassive black hole at its core. The black hole's mass correlates tightly with properties of the galaxy's central bulge, the dense spherical region of stars surrounding the center. Bigger bulge, bigger black hole, following a predictable ratio. That correlation suggests the two grow together somehow, influencing each other's development despite the black hole representing just a tiny fraction of the galaxy's total mass. Sagittarius A star weighs 4 million solar masses. The Milky Way contains perhaps 200 billion solar masses of stars, plus dark matter. The black hole is a rounding error in the total mass budget, yet it correlates with galactic structure. Why? How does something so relatively small leave such clear signatures on something vastly larger? The answer probably involves feedback. As black holes consume material and radiate energy, that energy heats surrounding gas, potentially regulating star formation throughout the galaxy. Active feeding periods might trigger bursts of star formation or quench it entirely depending on conditions. The mechanism remains speculative. Observations show the correlation exists, but causation proves harder to establish. Does black hole activity shape galactic evolution, or does galactic structure determine black hole growth? Probably both, in complex feedback loops spanning billions of years. Recent evidence from XRISM, Japan's X-ray space telescope, revealed something unexpected about Sagittarius A star. Molecular clouds floating near the galactic center glow faintly in X-rays, reflecting ancient outbursts from the black hole like cosmic mirrors. XRISM's energy resolution allowed astronomers to examine the fine structure of these echoes, determining what produced them. The analysis ruled out cosmic rays as the source. Instead, the clouds reflect an X-ray flare from Sagittarius A star itself, a light echo from somewhere between a few hundred and 1,000 years ago. That timing matters. It means our galaxy's central black hole was dramatically more active in the recent past, astronomically speaking. Today, Sagittarius A star ranks among the dimmest supermassive black holes known, barely accreting any material, generating almost no radiation compared to actively feeding black holes in other galaxies. Its low luminosity made it difficult to detect despite being relatively close, only 26,000 light-years away. But these light echoes suggest a different story. Within the last millennium, something triggered a major feeding event. The black hole suddenly consumed significant amounts of gas and debris, flaring hundreds of times brighter than its current state. Then it quieted down again, returning to its present dormant condition. What caused that outburst? Perhaps a star wandered too close and got torn apart, its remains spiraling inward. Maybe a gas cloud collapsed onto the accretion disk. The trigger remains unknown, but the evidence that it happened appears solid. NASA's IXPE telescope provided additional confirmation. Its polarization measurements suggest Sagittarius A star woke up roughly 200 years ago, devouring material in its vicinity before settling back into quiescence. These aren't isolated incidents. Black holes experience episodic feeding, alternating between active and quiet phases depending on available fuel. When material ventures within reach, accretion begins, radiation increases, and the black hole brightens. When the fuel runs out, activity drops. This cycling explains why some black holes appear extremely luminous while others, like Sagittarius A star, barely shine. It depends on timing, on whether we're observing during an active phase or a quiet one. The flares also provide opportunities to study black hole behavior indirectly. Direct observation of Sagittarius A star proves challenging because it's embedded in dense dust and gas. But watching its light reflected off surrounding clouds offers a workaround, letting astronomers analyze outbursts that occurred centuries ago. It's like studying lightning by watching the flash reflect off distant mountains rather than observing the bolt directly. Spin adds another dimension to black hole behavior. Sagittarius A star rotates at approximately 60% of the maximum possible rate according to measurements combining data from NASA's Chandra X-ray Observatory and the Very Large Array Radio Telescope. That rotation warps spacetime around it, dragging space itself into motion, creating what physicists call frame dragging. The effect distorts the region around the event horizon into an oblate shape, somewhat like a football rather than a perfect sphere. Previous estimates of Sagittarius A star's rotation varied wildly. Some suggested it wasn't spinning at all. Others proposed near maximal rotation. The new measurements narrow the range considerably, placing the spin at roughly 60% of maximum. Why does spin matter? Because it affects how material behaves near the black hole. A rapidly spinning black hole pulls surrounding spacetime along with it, influencing accretion disk dynamics, jet formation, and energy extraction mechanisms. Understanding spin helps explain why some black holes launch powerful jets while others don't, why accretion proceeds differently around different objects. Rotation also connects to how black holes grow. When two black holes merge, their spins combine according to complex rules determined by their masses, initial spin rates, and orbital geometry. The final spin of the merged object depends on whether the original spins aligned or opposed each other, whether they were parallel or tilted. Gravitational wave detections provide direct measurements of these properties. LIGO and its international partners, Virgo in Italy and CAGRA in Japan, now detect black hole mergers routinely, roughly one every 3 days. The network has captured around 300 confirmed mergers with more than 200 additional candidates awaiting analysis from the current observing run alone. That's more than double the number detected in the first 3 runs combined. The statistics are improving our understanding of black hole populations. Most mergers involve stellar mass black holes, objects formed from collapsing massive stars, typically ranging from a few to several dozen solar masses. The detections revealed that black holes can exist across a wider mass range than previously expected. Standard stellar evolution theory suggested a gap between about 65 and 120 solar masses where black holes shouldn't form. But LIGO detected GW190521, a merger between black holes of 85 and 65 solar masses, producing a 142 solar mass remnant. That falls directly in the supposed gap. Where did these objects come from? Possibly from earlier mergers. 2 smaller black holes combine, creating a larger one. That larger object eventually merges with another, building mass through successive generations. This hierarchical merging might explain how black holes reach masses that direct stellar collapse can't produce. It also hints at how supermassive black holes might have grown so large. Intermediate mass black holes, objects between stellar mass and supermassive scales, remain elusive. Theory predicts they should exist, bridging the gap between black holes of tens of solar masses and millions of solar masses. But finding them proves difficult. Candidates exist, identified through indirect evidence like gas cloud velocities or unusual accretion signatures, but confirmation remains tentative. The mass gap puzzles astronomers. Over cosmic time, collisions between stellar mass black holes should have created intermediate mass objects. Yet we don't see many confirmed examples. Why? Perhaps they're rare. Maybe they exist in environments where detection proves challenging. Or possibly something about black hole formation prevents easy population of that mass range. The search continues. Gaia BH3 provides one intriguing data point. This stellar mass black hole, discovered by the Gaia mission, weighs 33 solar masses, significantly larger than typical stellar black holes in the Milky Way, which average around 10 solar masses. Even Cygnus X1, previously the most massive stellar black hole known in our galaxy, only reaches 21 solar masses. Gaia BH3 sits unusually close, just 2,000 light-years away in the constellation Aquila, making it the second closest known black hole to Earth. Astronomers found it accidentally while reviewing Gaia data before an upcoming release. Nobody expected a high-mass black hole lurking nearby undetected. Its companion star provided crucial clues. Stars in binary systems tend to share similar chemical compositions because they formed from the same molecular cloud. Observations showed BH3's companion is extremely metal-poor, containing very few elements heavier than hydrogen and helium. That suggests the star that collapsed to form BH3 was also metal-poor. Theory predicts metal-poor stars lose less mass during their lifetimes through stellar winds, leaving more material available when the core finally collapses. That could explain how BH3 reached 33 solar masses while typical stellar black holes stop around 10. Astronomers had theorized this connection between metallicity and black hole mass based on observations of massive black holes outside our galaxy, but direct evidence linking metal-poor stars to high-mass black holes was lacking until now. BH3 provides that evidence, supporting models of how stellar properties influence remnant mass. The discovery also raises questions about how many similar objects might be hiding in our cosmic neighborhood, too distant or too faint for previous surveys to detect. The Milky Way itself holds secrets we're only beginning to uncover. At our galaxy's heart sits Sagittarius A*, a supermassive black hole weighing roughly 4 million solar masses. That's enormous compared to stellar mass black holes, but relatively modest for a galactic center. Sun galaxies harbor black holes tens of billions of times the Sun's mass. Holmberg 15A contains a black hole exceeding 40 billion solar masses. Phoenix A might reach 100 billion. Sagittarius A* looks almost quaint by comparison. Yet our black hole demonstrates something unexpected. Data from NASA's Chandra X-ray Observatory and the Carl G. Jansky Very Large Array reveals it spinning at about 60% of the maximum possible speed. That rotation warps spacetime around it into a football-like shape. Different research teams using various techniques have produced wildly different spin estimates over the years, ranging from zero rotation to nearly maximum. This recent measurement provides stronger constraints, showing substantial angular momentum. Why does spin matter? A rotating black hole drags spacetime along with it, creating regions where nothing can remain stationary. The faster the spin, the more pronounced these effects become. Material orbiting near a rapidly spinning black hole experiences different physics than material around a slowly rotating one. Sagittarius A* also appears remarkably quiet for its size. Most supermassive black holes at galactic centers actively consume surrounding material, glowing brightly across multiple wavelengths. Ours barely shines. It's one of the dimmest known supermassive black holes in the universe, visible only because of its proximity. 26,000 light-years separates us from the galactic center. That's close enough for detailed observations using instruments like the Event Horizon Telescope, which captured the first direct image of Sagittarius A*'s event horizon shadow in May 2022. That image revealed a glowing ring of hot gas orbiting the black hole at nearly the speed of light, with some material traveling at 30% of light speed just outside the innermost stable orbit. The dark region in the center isn't the event horizon itself but its shadow, where light deflection prevents any radiation from reaching us. But something strange happened recently. Well, recently in cosmic terms. Evidence from the XRISM Space Telescope suggests Sagittarius A* experienced a dramatic flare sometime within the past few hundred to 1,000 years. Several large molecular clouds floating near the galactic center act like cosmic mirrors, reflecting X-ray emissions from past events. Previous telescopes detected these reflections but lacked sufficient energy resolution to determine their source. XRISM changed that. The data strongly indicates these clouds are glowing in response to an ancient outburst from Sagittarius A*, a light echo from centuries ago. NASA's IXPE telescope independently found evidence suggesting the black hole woke up about 200 years ago, briefly devouring nearby material before returning to its current dormant state. What triggered this temporary feeding frenzy? One possibility involves an asteroid or gas cloud wandering too close, getting shredded and consumed. Another involves magnetic field lines in the accretion disk becoming tangled and suddenly reconnecting, releasing stored energy. On January 5, 2015, astronomers observed an X-ray flare from Sagittarius A * 400 times brighter than usual, the brightest ever recorded. The event lasted only briefly, but demonstrated our black hole can still produce violent outbursts when conditions align. Infrared observations captured something equally remarkable. Bright flares near Sagittarius A * showed orbital motion with a period of 45 minutes, give or take 15 minutes. That corresponds to material circling at 6 to 10 times the gravitational radius, moving in what appears to be a circularized orbit. The emission pattern suggests a polarized hot spot on the accretion disk, caught in a strong magnetic field and radiating intensely as it whips around the black hole. These observations help constrain the black hole's mass and spin, providing independent verification of measurements derived from stellar orbits. Speaking of stellar orbits, tracking stars near Sagittarius A * revolutionized black hole astronomy. Star S2 follows an elliptical path around the galactic center with a period of 15.2 years, approaching within 17 light-hours at closest approach. Watching S2 complete multiple orbits allowed astronomers to measure the central mass with extraordinary precision. Star S14 provided additional constraints, confirming the mass at roughly 4.1 million solar masses confined within a volume no larger than 6.25 light-hours in radius. Reinhard Genzel and Andrea Ghez shared the 2020 Nobel Prize in Physics for this work, demonstrating conclusively that Sagittarius A * must be a supermassive black hole. No other known object could pack that much mass into such a small space. But here's where things get interesting. Researchers recently identified something unexpected near the galactic center. A possible ultrafast pulsar spinning every 8.19 milliseconds, located close to Sagittarius A star. Pulsars are neutron stars, incredibly dense remnants of massive stars that emit beams of radiation from their magnetic poles. As they rotate, these beams sweep across space like lighthouse beacons. If the beam crosses Earth, we detect regular pulses. This candidate pulsar, if confirmed, would represent one of the most sensitive radio detections ever made in the turbulent galactic center region. More importantly, it would provide a unique laboratory for testing general relativity under extreme conditions. Tracking a pulsar this close to a supermassive black hole allows astronomers to make precise measurements of spacetime curvature, potentially revealing deviations from Einstein's predictions. The research, led by Karen I. Perez and published in the Astrophysical Journal, represents just the beginning. Confirming the pulsar and measuring its timing precisely requires additional observations. But if successful, this discovery could open new windows into black hole physics. The galactic center isn't our only nearby source of black hole discoveries. The Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way, recently revealed something unexpected. Astronomers traced the paths of 21 hypervelocity stars, objects moving so fast they'll eventually escape the gravitational pull of our galaxy and any nearby galaxies. These stars travel at millions of miles per hour, flung outward by powerful gravitational interactions. Where did they come from? About half trace back to Sagittarius A *, ejected when binary star systems ventured too close and got torn apart by tidal forces. One star gets captured into a tight orbit around the black hole while its companion rockets away at extreme velocity. But the other half didn't originate from our galactic center. They came from somewhere else entirely. Using data from the European Space Agency's Gaia mission combined with new theoretical models of stellar trajectories, researchers determined these stars originated in the Large Magellanic Cloud. That implies the presence of a previously unknown supermassive black hole in our satellite galaxy, massive enough to generate hypervelocity stars through the same tidal disruption mechanism. This represents potentially the closest supermassive black hole to the Milky Way outside our own galaxy. The Large Magellanic Cloud sits only about 160,000 light-years away, making it one of our nearest galactic neighbors. If it harbors its own supermassive black hole, that adds another laboratory for studying these objects up close. The discovery method itself proves fascinating. Hypervelocity stars are rare, requiring precise measurements to distinguish them from normal high-velocity stars. Gaia's unprecedented astrometric accuracy made this possible, tracking stellar positions and motions with extraordinary precision across the entire sky. By working backward from current trajectories, astronomers reconstructed where these stars originated. The fact that some trace back to the Large Magellanic Cloud rather than the Milky Way's center reveals the presence of another massive gravitational anchor capable of accelerating stars to escape velocity. This pattern of discovery continues across multiple scales and distances. Sometimes we find black holes through their gravitational effects on visible objects. Sometimes through their emissions when actively feeding. Sometimes through the traces they leave behind, like hypervelocity stars or gravitational wave signals. Each detection method reveals different aspects of black hole populations, building a more complete picture of how these objects form, evolve, and influence their surroundings. The techniques keep improving. Gravitational wave astronomy, barely a decade old, now routinely detects black hole mergers. The LVK network captured over 300 events across 4 observing runs, with more than 200 candidates identified in the most recent run alone. Every 3 days, on average, LIGO detects another merger. That detection rate would have seemed impossible just 10 years ago. Space-based telescopes push into new wavelength ranges, revealing black hole activity invisible to ground-based instruments. Astrometric surveys map stellar motions with unprecedented accuracy, uncovering hidden gravitational influences. Radio telescope arrays spanning continents achieve resolution sharp enough to image event horizon shadows. Each advance raises new questions while answering old ones. The volume of discoveries reflects how far observational capabilities have advanced. Consider what astronomers achieved in just the past few years. They imaged event horizon shadows around 2 different supermassive black holes. They detected hundreds of gravitational wave signals from merging black holes across cosmic distances. They traced hypervelocity stars back to their origins in neighboring galaxies. They found black holes in the infant universe, barely 500 million years after the Big Bang. They caught light echoes from past outbursts of Sagittarius A*, revealing episodes of violent activity hundreds of years ago. Each achievement required pushing instruments to their absolute limits. The techniques themselves reveal how indirect most black hole astronomy remains. You can't point a telescope at a black hole and simply see it. The object emits no light. Its defining characteristic is that nothing escapes once it crosses the event horizon. So astronomers look for effects. They watch stars orbit invisible points. They measure how light bends around massive objects. They detect gravitational waves from collisions billions of light-years away. They study accretion disk emissions, X-ray flares, radio jets. They trace stellar trajectories backward through time. Every detection method captures a different aspect of the same phenomenon. That diversity of approaches matters because black holes span an enormous range. Stellar mass black holes typically measure 10 to 20 solar masses, formed when massive stars collapse. Supermassive black holes at galactic centers reach millions or billions of solar masses, possibly growing through mergers and sustained accretion over cosmic timescales. Then there's the gap between them, where intermediate mass black holes should exist but remain frustratingly difficult to confirm. Scientists suspect a fourth category might lurk undetected: primordial black holes formed during the universe's earliest moments. Each type requires different detection strategies. The gravitational wave signal GW190521 demonstrated this perfectly. On May 21, 2019, LIGO detected the merger of black holes with masses of 85 and 65 solar masses. The resulting black hole weighed 142 solar masses, with 8 solar masses radiated away as gravitational waves during the collision. That final mass places the merged object squarely in intermediate mass territory, exactly where scientists expected to find missing link black holes. The detection confirmed that black hole mergers can produce intermediate mass objects, helping fill the gap between stellar and supermassive categories. Sagittarius A* itself continues revealing surprises. Recent observations show it spinning at approximately 60% of its maximum possible rate, fast enough to warp spacetime into a football shape around the event horizon. That spin rate comes from analyzing data from the Chandra X-ray Observatory and the Very Large Array. The rotation affects everything nearby, dragging spacetime and matter along with it. Previous estimates ranged wildly, from no rotation at all to near maximum spin. The new measurements narrow that uncertainty considerably. But here's something unexpected about our galactic center. Sagittarius A* ranks among the dimmest known supermassive black holes in the universe. It barely shines compared to active galactic nuclei in other galaxies. Most large galaxies host black holes that actively consume surrounding material, producing brilliant emissions across the electromagnetic spectrum. Ours sits relatively quiet, accreting material at a trickle rather than a flood. That dimness makes it visible only because of our proximity, 26,000 light-years away. Yet evidence suggests this wasn't always the case. The SRISM Space Telescope detected X-ray emissions from molecular clouds near Sagittarius A* that appear to be light echoes from a past outburst. These clouds act like cosmic mirrors, reflecting X-ray flashes from hundreds or even 1,000 years ago. The spectral characteristics rule out cosmic rays as the source, pointing instead to a powerful flare from the black hole itself. NASA's IXPE telescope found additional evidence suggesting Sagittarius A* experienced a major feeding episode roughly 200 years ago, consuming gas and other material within reach before settling back into its current quiescent state. These periodic outbursts might explain the relative quietness. Perhaps supermassive black holes cycle between active and dormant phases, gorging on available material during brief episodes then remaining dim for extended periods. If so, we're observing Sagittarius A* during a lull between feeding frenzies. The next active phase could happen tomorrow or 10,000 years from now. The timescales involve dwarf human observation windows. Scientists recently identified a possible ultra-fast pulsar spinning every 8.19 milliseconds near Sagittarius A star. If confirmed, this would provide an extraordinary laboratory for testing general relativity under extreme conditions. Pulsars are neutron stars, dense remnants of massive stars that emit beams of radiation from their magnetic poles. As they spin, these beams sweep across space like lighthouse beacons. A pulsar near a supermassive black hole would let astronomers make precise measurements of spacetime distortion, comparing the pulsar's clock against predictions from Einstein's equations. The turbulent environment near the galactic center makes finding pulsars difficult, requiring sensitive radio surveys to pick out signals from the background noise. The discoveries keep coming from ever more distant reaches of the universe. Astronomers found a supermassive black hole in the galaxy Canucks, LRD Z8.6, existing just 570 million years after the Big Bang. This object sits at the heart of a little red dot galaxy, one of the small, bright, extremely distant objects the James Webb Space Telescope routinely discovers. Another black hole in Kuiper's, LRD Z9 dates to only 500 million years after the Big Bang, with a mass of 38 million solar masses. These early supermassive black holes challenge formation models. How did they grow so large so quickly when the universe was barely 5% of its current age? Then there's ID 830, a black hole discovered from 12 billion years ago weighing 440 million solar masses, over 100 times more massive than Sagittarius A star. This object hosts a quasar accreting material at roughly 13 times the Eddington limit while simultaneously emitting strong X-rays and radio jets. That combination shouldn't exist according to standard models. Super Eddington accretion typically suppresses such emissions. The object might represent a rare transitional phase lasting only a few hundred years, captured by chance during observations. Or it might indicate gaps in theoretical understanding of extreme accretion physics. At the other extreme, astronomers recently discovered Gaia BH3, a stellar mass black hole weighing 33 solar masses. That makes it the most massive stellar black hole found in the Milky Way, far exceeding typical values of 10 to 20 solar masses. Located just 2,000 light-years away in Aquila, it's the second closest known black hole to Earth. The discovery came while reviewing Gaia data for an upcoming release. Nobody expected to find such a massive black hole lurking nearby. Analysis of its companion star revealed extremely low metallicity, meaning very few elements heavier than hydrogen and helium. This supports theories that metal-poor stars lose less mass during their lifetimes, leaving more material to collapse into high-mass black holes after death. Perhaps the most massive black hole ever observed sits 5 billion light-years away, weighing approximately 36 billion solar masses. That's 36,000 times the mass of Sagittarius A star. It has competition from Phoenix A, the central black hole of the Phoenix cluster, estimated around 100 billion solar masses. These ultramassive objects push the boundaries of black hole physics, raising questions about formation mechanisms and growth limits. An international team recently discovered a dense cluster of supermassive black holes dating back 10.8 billion years, dubbed the Cosmic Himalayas. This represents the highest concentration of active black holes ever observed from that epoch. The surrounding galaxy and gas distributions deviate from standard cosmological models, suggesting either a uniquely special region or a rare moment when many black holes activated simultaneously. In 2025, several papers presented images of surprisingly straight stellar streaks within galaxies, convincing evidence for runaway black holes. A million or billion solar mass object traveling through a galaxy creates enormous disruptions to surrounding stars and gas, leaving distinctive trails. Each discovery adds context to the others. Hypervelocity stars from the Large Magellanic Cloud connect to stellar mass black holes like Gaia BH3 through shared formation mechanisms. Gravitational wave detections from LIGO inform models of intermediate mass black hole populations. Early universe observations from JWST constrain supermassive black hole growth rates. The dimness of Sagittarius A* contrasts with luminous quasars like ID 830, revealing diversity in accretion behavior. Light echoes from past outbursts demonstrate that even quiet black holes experience violent episodes. The pattern emerging from all these observations suggests black holes aren't rare cosmic oddities but fundamental components of galactic evolution. Almost every large galaxy harbors a supermassive black hole at its center. Stellar mass black holes form regularly from massive star collapse. Intermediate mass black holes likely exist in significant numbers despite remaining difficult to confirm. The universe produces these objects continuously across all mass scales and cosmic epochs. Understanding them means understanding how galaxies form, how matter behaves under extreme gravity, and how spacetime itself responds to concentrated mass energy. From our vantage point 26,000 light-years from Sagittarius A*, we're positioned perfectly to study these phenomena. Close enough to observe details impossible to resolve in distant galaxies. Far enough to remain safe from direct effects. The discoveries made in the past decade represent just the beginning. As instruments improve and detection techniques advance, the catalog of known black holes will continue expanding. Each new object adds another piece to an increasingly complete picture of how these cosmic engines shape the universe around them. The picture taking shape across decades of observation reveals something remarkable. Black holes aren't exotic exceptions but standard equipment throughout the cosmos. Every major galaxy appears to harbor a supermassive version at its core. Stellar remnants produce smaller ones routinely when massive stars exhaust their fuel. The gap between these scales, once puzzling, now shows signs of filling in through hierarchical mergers detected by gravitational wave observatories. What changed wasn't the universe but our ability to see it clearly. LIGO transforms spacetime ripples into measurable signals. Gaia tracks stellar motions with precision that would have seemed impossible decades ago. The Event Horizon Telescope coordinates observations across continents to achieve resolution sharp enough to image event horizon shadows. JWST pushes deep into cosmic history, finding black holes that formed when the universe was barely 500 million years old. Each instrument reveals aspects invisible to others, building complementary views of the same phenomena. The discoveries keep reshaping assumptions. Sagittarius A*, once thought permanently dormant, shows evidence of violent outbursts just centuries ago. The Large Magellanic Cloud, assumed too small to host a central supermassive black hole, apparently contains one massive enough to fling stars toward intergalactic space. Stellar mass black holes reach masses that stellar evolution models suggested shouldn't exist. Early universe black holes grow faster than standard accretion physics allows. Intermediate mass objects remain scarce despite theoretical predictions they should be common. These contradictions drive progress. When observations conflict with models, something has to give. Usually it's the models. Theories get refined, expanded, sometimes discarded entirely when they can't accommodate new data. That process accelerates as detection rates improve. LIGO now finds mergers every few days. Gaia continues updating its stellar catalog with increasing precision. Radio telescope arrays add more observatories to their networks, sharpening resolution further. Space-based instruments push into wavelength ranges unavailable from the ground. The hypervelocity stars traced back to the Large Magellanic Cloud demonstrate how indirect evidence can reveal hidden structures. No telescope directly imaged that galaxy's central black hole. Instead, astronomers worked backward from stellar trajectories, reconstructing where those objects must have originated. The logic was straightforward. Stars moving that fast require powerful gravitational slingshots. Only supermassive black holes generate forces strong enough to accelerate stars to escape velocity. Half the hypervelocity stars came from Sagittarius A star. The other half pointed elsewhere. Follow those trajectories back, and they converge on the Large Magellanic Cloud. Similar detective work revealed Gaia BH3. The black hole itself emits nothing. It's invisible except for its gravitational influence on a companion star. But that influence was enough. Gaia measured the companion's motion with such precision that astronomers could calculate the unseen object's mass. 33 solar masses, far heavier than typical stellar black holes. The companion's chemical composition provided additional clues, showing extremely low metallicity that supported theoretical predictions about how massive black holes form from metal-poor stars. Even Sagittarius A*'''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''' Black holes' outburst centuries ago would have remained unknown without molecular clouds nearby acting as cosmic mirrors. Previous telescopes detected those reflections but couldn't resolve enough detail to determine their source. XRISM's improved energy resolution changed that, revealing spectral signatures consistent with X-ray emissions from Sagittarius A** itself rather than cosmic rays or other sources. These techniques work because black holes, despite emitting no light directly, interact with everything around them. Material falling inward heats through friction until it radiates across the electromagnetic spectrum. Tidal forces tear apart objects that venture too close. Gravitational lensing bends light from background sources. Spinning black holes drag spacetime itself into motion. Each effect leaves observable traces for instruments sensitive enough to detect them. The diversity of black hole masses, from stellar remnants to ultramassive monsters, suggests multiple formation pathways operating across cosmic history. Stellar collapse produces the smaller ones. Sustained accretion over billions of years might grow some supermassive versions. Direct collapse of massive gas clouds could seed others. Hierarchical mergers build intermediate mass objects from smaller progenitors. Primordial black holes, if they exist, would have formed during the universe's first moments through different mechanisms entirely. Understanding which pathways actually operate requires observations spanning the full range of masses and cosmic epochs. That's where the recent explosion of detections proves valuable. Each gravitational wave signal from LIGO adds data points about stellar mass black hole populations and merger rates. Each early universe black hole found by JWST constrains supermassive formation timescales. Each intermediate mass candidate helps fill the gap between extremes. Slowly, the full distribution takes shape. Sagittarius A** occupies a special position in this story. It's close enough to study in unprecedented detail but representative enough to inform understanding of supermassive black holes generally. The spin measurements, orbital dynamics of nearby stars, episodic activity revealed through light echoes, and eventual imaging of its event horizon shadow all contribute pieces to broader puzzles about how these objects behave. The possible pulsar near the galactic center, if confirmed, would add another tool for probing spacetime structure under extreme conditions. But proximity brings limitations too. Sagittarius A**''''''''''''''''''''''''''''''' accretion disk changes on timescales of minutes, making it harder to image than more distant but steadier objects like M87 star. The galactic center's crowded, turbulent environment complicates observations. Dust and gas obscure some wavelengths entirely. Trade-offs exist between studying nearby objects in detail versus observing more distant ones that remain stable long enough to capture clean data. The Large Magellanic Cloud's black hole, if confirmed, would provide another nearby laboratory with different properties. Comparing how black holes behave in dwarf galaxies versus major ones like the Milky Way tests whether the correlations observed between black hole mass and galactic properties hold across different scales. Early results already suggest some surprises. The Large Magellanic Cloud lacks a prominent bulge, yet apparently hosts a supermassive black hole anyway. That challenges models assuming tight coupling between bulge properties and central black hole mass. Looking ahead, the detection rate will continue accelerating. LIGO and its partners are planning upgrades that will extend their sensitivity deeper into the universe. The Event Horizon Telescope keeps adding observatories to its network, improving resolution and possibly enabling video rather than static images of accretion disk dynamics. Gaia will release increasingly refined astrometric catalogs as observations accumulate. JWST continues pushing further into the early universe, finding black holes from ever earlier cosmic epochs. New space telescopes in development will cover wavelength ranges current instruments can't access. Each improvement reveals previously invisible details. The question isn't whether we'll find more black holes, but how many and what surprises they'll contain. Based on recent patterns, expect the unexpected. Expect black holes in places they shouldn't be, with masses outside predicted ranges, behaving in ways models don't anticipate. Expect gaps in understanding to become apparent as observations outpace theory. Expect the census of known black holes to grow from hundreds to thousands to eventually millions as automated surveys scan the sky continuously. The 21 hypervelocity stars that revealed the Large Magellanic Cloud's hidden black hole represent a tiny fraction of such objects. Most hypervelocity stars remain too faint or distant to detect with current instruments. As surveys improve, that population will expand, potentially revealing additional hidden black holes in other satellite galaxies or even in intergalactic space. Each discovery adds context to the broader picture of how galaxies evolve and interact. That broader picture shows black holes playing central roles in cosmic structure formation. Their gravitational influence shapes galactic centers. Their feeding generates radiation that regulates star formation across entire galaxies. Their mergers produce gravitational waves that ripple across spacetime. Their jets inject energy into surrounding gas on scales spanning hundreds of thousands of light-years. They're not passive observers but active participants in galactic evolution. Understanding them means understanding how matter behaves under conditions impossible to recreate in laboratories. The pressures, temperatures, and gravitational fields near black holes exceed anything achievable on Earth by factors of billions or more. General relativity predicts how spacetime responds, but testing those predictions requires observations of real black holes under extreme conditions. The possible pulsar near Sagittarius A* could provide exactly that test, assuming confirmation and precise timing measurements prove feasible. Every technique developed for studying black holes finds applications elsewhere. Gravitational wave astronomy opened windows into neutron-star mergers and potentially other phenomena. Astrometric precision from Gaia enables studies of stellar populations, galactic structure, and dark matter distribution. Radio interferometry techniques used by the Event Horizon Telescope apply to other astronomical targets. X-ray spectroscopy methods refined for black hole observations work for studying other high-energy phenomena. The tools built for one purpose prove useful for many. The pace of discovery now exceeds the pace at which individual humans can absorb new information. Papers describing black hole detections appear weekly. Each adds details to an increasingly complex picture that no single person fully comprehends. That's why collaboration matters. Teams spanning institutions and countries combine expertise from different fields. Theorists work with observers. Instrument builders coordinate with data analysts. The discoveries emerge from collective effort rather than individual brilliance. Sagittarius A* sits at the center of our galaxy, massive and mysterious, spinning at 60% of maximum speed, occasionally flaring to life before settling back into quiescence. 26,000 light-years away, close enough to study in detail, far enough to remain safely distant. Around it, stars orbit at significant fractions of light speed. Molecular clouds reflect ancient outbursts. A possible pulsar spins nearby. And we watch, measuring, calculating, slowly piecing together how this object formed, grew, and shapes its surroundings. The same process plays out across the universe, in every galaxy containing a central black hole, each one adding data to the growing understanding of how these cosmic engines operate.